For every positive integer n, if a sub 1, a sub 2, a sub 3, and so on, and b are any sets, then the union from I equals 1 to n of a sub I minus b is the same set as the union from I equals 1 to n of a sub I, all minus b. Now we're trying to prove that two sets are equal to each other, which means that we first have to show that this set is a subset of the other set. That's the first part of this proof. And to do that, we're going to let x be an arbitrary element from this first set. Now we can unpack what this means by expanding this union. We can iterate I from I equals 1 to I equals n. So by definition of union, x is an element of a sub 1 minus b, or x is an element of a2 minus b, or, and so on, or x is an element of a sub n minus b. Now what we're going to show is that regardless of which of these is the true statement, we can still prove that x is an element of this set here. Now this is WLOG, which means without loss of generality. We're going to say that x is an element of a sub j minus b, where j is some number that's an integer, and j has to be between these two index values, I equals 1 and I equals n. So what we're doing here is we're just saying, let's just pick a random one, a sub 2 minus b or something like that, a sub j minus b. J could be any integer, and it doesn't really matter what j is. What we're going to show is that x is still an element of the set on the right side here. Now we can unpack what it means for x to be an element of a sub j minus b. So by definition of set minus, x is an element of a sub j, and x is not an element of b. Now we have that x is not an element of b, which we're going to need in a second here. But we need to show that x is an element of the union from I equals 1 to n of a sub I. And the way we're going to do that is we're going to do addition. Now keep in mind, addition is a rule of inference. It allows us to say that if P is true, then P or Q must also be true, regardless of what Q is. So right now we know that A sub j is true, but what we can do is we can say, by addition, x is an element of A sub 1, or x is an element of A sub 2, or x is an element of A sub 3, or and so on, or x is an element of a sub j, or x is an element of a sub n. So since x is an element of a sub j, by addition we can say x is an element of a sub 1, or x is an element of a sub 2, or x is an element of a sub 3, and so on, or x is an element of a sub j. This is the one that we know to be true at this point, or, and then so on, or x is an element of a sub n. Now we actually don't know whether or not all of these other statements are true, but we don't need to know that they're true according to the rule of inference addition. So this whole statement is true precisely because this part of the statement is true. But we need to assert all of these things because then we can use the definition of union. This means that x is an element of the union of all of these sets. And so now we have x is not an element of this, and x is an element of this. And so x is an element of the union from I equals 1 to n of a sub I, all minus b. So far what we've shown is that this set here is a subset of this set here. What we need to show now is that this second set is a subset of the first set. So now we're going to do everything backwards. So now we're going to let x be an element of this set, the union from I equals 1 to n of a sub I minus b. But then we can just basically do the same proof as the first part, but backwards. We can unpack the definition of the set minus. So by definition of set minus, this says that x is an element of the union from I equals 1 to n of a sub I, and x is not an element of b. Next, we can unpack the definition of union. X is an element of a sub 1, or x is an element of a sub 2, or x is an element of a sub n. And that is the definition of union. And so we can say that without loss of generality, x is an element of a sub j for some integer j. And j is some integer between 1 and n. But we're going to show that it doesn't matter. So since x is an element of a sub j and x is not an element of b, then by definition of set minus, this means that X is an element of A sub j minus B. But we want to show that X is an element of the union from I equals 1 to n of A sub I minus B. And so to get there, we can use addition, which is a rule of inference. So by addition, X is an element of A sub 1 minus B, or X is an element of A sub 2 minus B, or ... or X is an element of A sub j minus B. This is the one that we know to be true, and this is what we're adding onto with the rule of inference addition. Or ... or X is an element of A sub n minus B. But then we can use the definition of union to say that X is an element of the union from I equals 1 to n of A sub I minus B. And that's what we wanted to show. So that proves that the second set is a subset of the first set. So we started by proving that the first set is a subset of the second set, and then we proved that the second set is a subset of the first set, which means that both of these sets are equal to each other by definition of set equality. Thanks, everyone, and I'll see you in the next video.